Okay, we continue with our problem. All right. Okay, so we're on part C. Okay, so in part C, we suppose that x sub k plus 1 equals a times x sub k for k equals 0, 1, 2, etc. And we have to prove that the limit as k goes to infinity of x sub k is equal to v1. Strange. Okay, so we suppose x sub k plus 1 equals a times x sub k for k equals 0, 1, 2, etc. So we've seen that this implies that x sub k is equal to a to the k x naught for k equals 0, 1, 2, etc. Okay. All right, now from the previous part, we've deduced that we have that x naught is c1 v1 plus c2 v2 plus c3 v3, and we know c1 is equal to 1. So x naught is v1 plus c2 v2 plus c3 v3. So that's equal to a to the k v1 plus c2 a to the k v2 plus c3 a to the k v3. And okay, since v1 is an eigenvector of a with eigenvalue 1, this will be 1 to the k v1. And since v2 is an eigenvector with eigenvalue lambda 2, this will be lambda 2 to the k v2. And likewise, the last one will be lambda 3 to the k v3. So that's since v1, v2, v3 are eigenvectors of A with eigenvalues lambda 1 equals 1, lambda 2, and lambda 3. So it's important to give the reason here, what's going on. Okay, so now we can take the limit as k goes to infinity of x sub k will be the limit as k goes to infinity of, okay, so the first term is just v1, and then we have c2 lambda the 2k v2 plus c3 lambda the k v3. Okay, which is that. Now, this is just constant, so that's v1. The limit of these two will be the 0 vector, and that simplifies to v1 since the absolute value of lambda 2 is a half, which is less than 1, and the absolute value of lambda 3, which is 2/5, is less than 1. And that means the limit as k goes to infinity of lambda 2 to the k equals limit as k goes to infinity of lambda 3 to the k equals 0. Reason being is lambda 2 and lambda 3 have absolute value less than 1. So these two scalars go to 0, which means this vector goes to the 0 vector, and that vector goes to the 0 vector, and this whole limit is equal to v1, which is what we were asked to show. Okay, so now we need to find the next problem. All right. Okay, so in problem number 3, we're given that this matrix has eigenvalues 1 and 5, and we're asked to find an invertible matrix P such that P inverse AP is equal to D, a diagonal matrix, and we're asked to find the matrix D. Okay, so this was question 3. So we know the matrix A has eigenvalues lambda 1 equals 1 and lambda 2 equals 5. Okay, so we need 3 independent eigenvectors. So the idea is to find a basis for each eigenspace. Okay, so the first eigenspace is E1, and what we need to do is solve A minus I times X equals 0. Okay, so that's equivalent to a homogeneous system. Okay, 0, 0, 0. We subtract 1 from the diagonal, so we'll have 1, 2, negative 1, 1, 2, negative 1, negative 1, negative 2, and 1. Okay, so it's pretty clear that this matrix reduces to the following 0, 0, 0, 0, and 0, 0, 0, 0. In fact, you could multiply row 1 negative 1 added to row 2 and add row 1 to row 3, and we'll get 2 rows of zeros. So we see 1 pivot, and we see that x2 and x3 are free variables. Okay, so we write our general vector x1, x2, and x3 in terms of our free variables x2 and x3. So the first equation says x1 is negative 2x2 plus x3, x2 is x2, and x3 is equal to x3. So we can factor out an x2 and an x3 and get a linear combination. Here we'll get the vector minus 2, 1, 0, 1, 0, 1. So usually we'll just put x2 equal to a parameter t and x3 equal to a parameter s, but we can leave it like this. But this just shows you that these two vectors here form a basis. So minus 2, 1, 0, and 1, 0, 1 will be a basis for the first eigenspace, E1. Okay, so we're on page 3. Okay, so we have 2 eigenvectors. So it remains to find a third independent eigenvector. So we look at E5, and we could solve A minus 5 times the identity, x equals 0. Okay, so that's a linear system, homogeneous. Okay, we subtract 5 from the diagonal. We're going to get negative 3, 2, negative 1, 1, negative 2, negative 1, and negative 1, negative 2, negative 3. Okay, so let's just swap the first 2 rows around. Okay, so multiply the first row by 3 and add it to the second. We're going to get 0, negative 4, negative 4, 0. And down here we add the first row to the third row, we're going to get 0, negative 4, negative 4, 0. So that clearly reduces to 1, minus 2, minus 1, 0, 0, 1, 1, 0. And the last row is a row of zeros. Okay, now we could multiply the second row by 2 and add to the first, and we'll get 1, 0, 1. And here we'll get 0, 1, 1, 0, 0, 0. Okay, we have two. Whoops, I've gone off the page. Sorry about that. Let's move it up a bit. Okay, so that's what we got. And we see that x3 is a free variable. Our solution vector x is x1, x2, and x3. So x1 has to be negative x3. x2 is negative x3. And x3 is x3. We factor out an x3, and we got a vector minus 1, minus 1, 1. And so we have the vector negative 1, negative 1, 1 will form a basis for E5. Okay, so is the basis for E5. Okay. Okay, so it follows, this procedure follows that we have two basis vectors from the first eigenspace and a third eigenvector from the last eigenspace. Those vectors were minus 1, 1, 0, 1, 0, 1, and negative 1, negative 1. And this procedure, the usual procedure guarantees that these are independent, linearly independent. Eigenvectors with eigenvalues 1, 1, and 5. So that means we can create a matrix P such that P inverse AP is a diagonal matrix. And on the diagonal we'll have the eigenvalues 1, 1, 5, zeros everywhere else. And our matrix P is just formed from the three eigenvectors, minus 2, 1, 0, 1, 0, 1, negative 1, negative 1. And this first guy is eigenvalue 1, eigenvalue 1, eigenvalue 5. So that's why we have 1, 1, 5. It's not necessary to check that P inverse AP is this. The theory guarantees this, but you could check it if you had time.